In this video, we're going to cover the fundamentals of functions and relations. In particular, we're going to look at set notation. We're going to cover what is set notation, why do we need to know about it, and what are the ways in which set notation is used in VCE math methods. So what exactly is set notation? Set notation is an agreed upon set of symbols that are used to describe groups or sets of things mathematically. For example, we might be interested in the set of hearts in a 52-card deck, or perhaps we're interested in the number of pens in a box of office supplies. In both examples, we're fundamentally talking about the same thing. We're interested in a group of objects. Set notation allows us to ignore the specifics and just focus on the underlying mathematics. So why do we need to know set notation? Well, in short, it's because you need to know how to read this. This came from the VCE 2022 exam, and if you don't even know how to read the question, you can't even begin to answer it. So if you struggle to read this, then this video is for you. Okay, so how do we define a set in mathematics? A set is a collection of items. Items that belong to the set are called elements, or sometimes referred to as members of that set. If some item X belongs to the set A, we can write this using the expression to my left, which reads X is an element of A, where X is the item and A is the set that it belongs to. You can see what this looks like visually with a Venn diagram. You can see that the element X is entirely contained within the circle labelled A. This is to symbolise that X is an element of the set A. For example, we could say that the ace of hearts, AH, is an element of the set of all playing cards, C. If an item doesn't belong to a set, we use the same expression as before, but this time we put a slash through the symbol. Here is a Venn diagram of what that looks like. Notice that X is now no longer contained by the circle A. This is thus symbolising that X is no longer an element of that set. Now, let's talk about subsets. Suppose we have two sets, A and B. If all the elements of B also belong to A, then B is considered a subset of A. This is written mathematically using this symbol here, this weird inverted U looking thing. And the Venn diagram above shows what this looks like visually. Notice how the set B is entirely contained within the set A. Again, using playing cards as an example, you could have the set of 52 playing cards as the set C, and a subset of that could be the set of hearts in that deck. There are no hearts that exist outside the set of all playing cards unless you're trying to slip some cards under the table at a game of poker, in which case, don't at me when you get caught cheating. It wasn't my idea. Now we can talk about intersection of sets. Suppose again we have two sets A and B. If only some of the elements of A and B exist in both sets, then we say that A and B intersect. This is written mathematically using this expression, which reads A intersection B. Again, we have a Venn diagram to show what this looks like visually. Notice how the elements 5, 1 and 3 all belong in the middle, that intersection area, and all the other elements belong outside that set. For example, we could have the set of hearts and the set of aces. Now there is an intersection between these two sets, but not all the elements belong to each other. Only the ace of hearts belongs to both sets. If two sets have no intersection, we call them disjoint sets. Now this is expressed mathematically using the null set symbol. Now a real life example of this could be in a box of stationery supplies. You could have the set of erasers and the set of sharpeners. There are no sharpener erasers unless I'm mistaken, in which case get in the comments to let me know. Alrighty, so now we can talk about the set difference. The set difference is simply all the elements that belong to one set A that do not belong to the other set B. Now this is written mathematically using a backslash. And again, you can see what this looks like visually. If the sets have an intersection, then this is accounted for with the set difference. People like to label things, and mathematicians are clearly no different, as they gave different kinds of numbers their own unique sets. This diagram below illustrates the relationship between the different kinds of numbers. This diagram might not make much sense for now, but by the end of this video my promise to you is that it won't look like total nonsense, only mild nonsense. So let's start the discussion with natural numbers. Natural numbers are the set of all positive whole numbers, starting from 0 to 1 to 2 to all the way up to infinity. The set of all natural numbers is denoted by this fancy letter n. Now we move on to integers. Integers are like natural numbers in that they go up to positive 1, 2, 3, up to infinity, but they can also be negative. So we have negative 1, negative 2, negative 3, down to infinity. And the set of all integers is denoted by this capital letter Z. And before we move on, I want to highlight again that the set of natural numbers is actually entirely contained in the set of integers. So in this way we can say that the set of natural numbers is a subset of the set of all integers. So hopefully this diagram is starting to make just a bit more sense. So moving on to rational numbers. Simply put, rational numbers are just fractions. They have some numerator a denominator b. The numerator and denominator must be integers, and the denominator must be non-zero. Because in mathematics we can't divide by 0, or if we do, we call the result undefined. The set of all rational numbers is defined by the capital letter Q. And before we move on, rational numbers are fractions, but that doesn't mean they can't be whole numbers as well. Consider the case where a, the numerator, is 3, and b, the denominator, is 1. This simplifies to just 3, which is a whole number. So again, we see this relationship where the set of integers is a subset of the set of rational numbers. Now we can discuss irrational numbers. Irrational numbers are actually a special case. They are numbers that cannot be perfectly represented as a fraction. This could be the number pi, which has an infinitely repeating set of decimals. In fact, there are actually super nerdy competitions to see who can memorize the most digits of pi. Now, there are other examples of irrational numbers, like root 2, or pretty much any other square root. Now, there actually isn't an agreed upon letter for the set of rational numbers. This is probably because it breaks the pattern earlier we were talking about, where each of the previous sets is a subset of the next one, but they are still important to remember. We finalise our discussion on sets of numbers with real numbers. Real numbers are the set of all rational and irrational numbers. For math methods purposes, you can basically think of this as the set of all possible numbers. That isn't strictly true, but for math methods, that's all you really need. And so once again, we have the diagram that explains the relationship between sets of numbers. So we can see that the sets of numbers pretty much act like Russian nesting dolls, starting at the real numbers and ending at the natural numbers. And that brings us to the end of this video on set notation. If you found this video helpful and would like to see more, I have a Google Drive containing written versions of lectures like this, but covering the entire Year 12 Math Methods syllabus. Just click the link in the description below and it will take you to my website. Just scroll down a little and click this heading to get access. No opt-in required, free of charge. In the next video, we'll cover the rest of the fundamentals of functions and relations. And by the end of that video, you'll be well prepared to get into the good stuff. See you there.